Now, if we want to get the Gibbs free energy at 1000 degrees Kelvin, okay, it's the same equation. Okay, so but I need to find my enthalpy of reaction, my standard enthalpy of reaction at 1000 degrees Kelvin minus 1000. Okay, so times by the entropy of reaction at 1000 degrees Kelvin. Okay, so, and the way I'm going to do that is I'm going to use my reaction path. And sorry, I just realized I've got the wrong temperature. Here I'm actually interested in 1200 degrees Kelvin. Okay, and 1 minus 1. Okay, 1200 degrees Kelvin. So to get to 1200 degrees Kelvin, I need to use a path. Okay, so 1200 Kelvin. Okay, so I've got carbon monoxide gas plus half oxygen gas. Okay, so this is the delta H, or the delta of the reaction that I'm interested in. Okay, goes to CO2 gas. And so to get from this point to this point, what I'm going to do is cool this down to 298 degrees Kelvin, and then form CO2, and then heat this up again. Okay, so this is the path that I've chosen because my data's tabulated at 298.15 Kelvin. So that means that I can calculate the changes in enthalpy and the changes in entropy at this temperature. And so what I need is to calculate changes for this step, 1, 2. I'll call this delta 3, and then over here is delta 4. Okay, so if I have a look at these 3 steps here, then I can see that all 3 steps are on the left hand side they're cooling steps, on the right hand side they're heating steps. So I can say that delta 1H plus delta 2H plus delta 3H, okay, is just equal to the sum of the stoichiometric coefficient of each component I. And so that's equal to and I'm integrating that from 298.15 to 1000 Kelvin. Now I'll make myself a bit of room here. Okay, and so that's 1000. Okay, and so that's equal to the CP of CO2 minus half of the CP of O2 minus the CP of CO. Okay, so my stoichiometric coefficients are in here: 1, negative a half, and negative 1 in here. Okay, so when I go and get my data from Lee, okay, so I get my heat capacity data here. Okay, so in these last few terms here, and then I go back up to CO and CO2. So I get my heat capacity data in here. Then I can go back and I can add my heat capacity data up. Okay, so I'm just going to tabulate it just to make it easy to add. Okay, so So these are my coefficients, so A, B, and C. Okay, so this is, let me just double check. So times 10 to the 3 and times 10 to the minus 5 times 10 to the 3, and that's times 10 to the minus 5. Okay, just to make it nice and easy. And so then I've got CO, O2, and CO2. I'll add in my stoichiometric coefficient here. So -1, -0.5, and 1. And then my heat capacity constants. And for oxygen, okay, now 4 and then 4.18, and then my final one here, my C's, and then -1. Okay, so for my sum of VI CP, okay, stoichiometric coefficient times my heat capacity, then what I get is, so just underline that, so 0.75, 2.85, and then -7.245. So so my sum of the heat capacity, or my delta H, oops, get rid of that. Okay, so my delta H here, okay, is equal to delta 1 H plus delta 2 H plus delta 3 H is equal to the integral of that term. Okay, so now that I've got that, I know that that's equal to the integral to 1200, not 12,000, of 0.75 plus T minus okay, took the wrong number, minus 7.245 times 10 to the 5 divided by T squared. Okay, so to do this integral, I'm going to use MATLAB, and so I evaluate this integral in MATLAB. I'll put the code up on Blackboard, and so I find that the delta H for this is only 1507 joules per mole. Okay, so per mole of carbon dioxide. Now for delta S, we know that that the delta S will be equal to, for those heating steps, delta 1 S plus delta 2 S plus delta 3 S. Okay, and so that's equal to the integral from 298 to 1200 of the sum of CP over T. Okay, so we have to remember to, I missed a couple of DTs there, and so we have to remember to divide by T before we integrate. We can't divide by T afterwards. Okay, so this is equal to the integral of plus 3 Okay, and there's to T in there. So again, I'm going to evaluate this in MATLAB, and what we get is a very small change, or a very small net change in the entropy. Okay, corresponding to the small net change in the enthalpy. So what we get is that the standard heat of reaction at 1200 Kelvin is equal to the value that we had before. Okay, so it's delta 3H, okay, plus the delta that we calculated for the heat of reaction. So this term here is equal to this term up here. Okay, and this term here is our enthalpy of reaction at 298 Kelvin. Okay, so when I add those two things together, then what I get is minus 197.4 kilojoules per mole. Okay, so that compares with the 298 value of minus 195.9. So the heat of reaction changes very, very little, because the heat capacities almost cancel each other out. Similarly, for the entropy of reaction at 1200 Kelvin, then what we have is the same step for the entropy, plus the entropy that we just changed, that we just calculated for all those heating steps. Okay, so that's this term here. And so when we do that, then we get minus 86.4 minus 1.28. Okay, so that's approximately equal to minus 87.7 joules per mole Kelvin. Okay, so again, a very small change in the entropy. So since we've had a very small change in the entropy and a very small change in the enthalpy, then we'll expect that we'll see a very small change in the Gibbs free energy of reaction. Okay, so 400, so plus 1200 degrees times by 87.7. Okay, so what we get is about minus 92,000 joules per mole, so, or approximately minus 92 kilojoules per mole. Okay, so we don't get a small change, even though we have a small change in delta H and delta R, because don't forget that temperature is changing as well. Okay, and so probably if we went to a high enough temperature, then eventually this delta Gibbs free energy of reaction would eventually become positive, and it would become non-spontaneous. But at 1200 degrees Celsius, it's still negative, and therefore it's still spontaneous at this temperature. Thank you.